This is Mrs. Schroeder, and we are going to talk about solutions. This is Chapter 13. We're going to cover Section 1 and a little bit out of Section 2. Objectives for this section would be understanding solutions, suspensions, and then this new word, colloids. Talking about techniques chemists use to separate mixtures, so we can do some labs with it. And we're also going to today learn a calculation called parts per million. That's the third objective of the day. Substances can be either pure substances or they can be mixtures. If you remember that from earlier in the year. Mixtures can be either heterogeneous or homogeneous depending on the particles. So hopefully you remember what those terms are. There's some key vocabulary. You need to know these. If you don't, make some flashcards up. These words: solution, suspension, solvent, and solute. They will be used throughout this chapter, and you will need to know what they mean. So take a minute, pause the video if you need to at this point, and stop and write these things down. Suspensions are things that the particles, they look at first in this one. First, it looks like it's all one phase. You see this murky colored water. But after a while, if you have this glass of murky colored water and you leave it sitting without stirring it, you'll see this murky stuff, the clay, begins to settle out along the bottom. And that's what's kind of down here. Initially, if you stir it up or shake it up, they'll get mixed back up and you'll get these clay particles surrounded by water. And you'll see this suspension. A suspension will settle if you leave it over time. A solution, on the other hand, will not. If I put sugar in water and stir this thing up, it becomes a solution. No matter how long I let that solution go, as long as it's covered and the water's not going to evaporate, it's going to remain in solution. It will not settle back out to here without taking the water away. If I look at this on a closer scale, I notice that my sugar and my water particles are nearly the same size. This is part of how this works. Over here my clay was much bigger than my water, but my sugar and water are about the same size. So solutions, we want to think about things as having particles relatively the same size. And this graphic shows you, we use particle size less than 10 to the -7th centimeters. Very small. That would be our true solution. Our suspensions are over 10 to the -5th centimeters are your suspensions, things that will settle out. We have this in-between thing. If I'm between 10 to the -7th and 10 to the -10th, I have something called a colloid. Colloids are heterogeneous mixtures because I have two distinct phases here, but they're stable. They will not settle out. If I can leave it standing for a long period of time and it won't settle out and show that particles on the bottom. Common example of this is milk. Milk has these fat molecules in them, which are these fat globules, and proteins are very big. They are not the same size as water. They're much bigger. They're not a true solution, but they don't settle out. You don't come in to have to shake your milk up before you drink it. It's all one phase. Okay. It also works better if they have some kind of electric charge. You know, you're partial negative or partial positive, because that will help to repel those particles. If all the particles have a partial positive on them, they're going to be repelled. Solvent-solvent combinations can be gas-gas, gas-liquids, gas-liquid, or solid. All of these things can be a solution with a different solvent and solute. Mixtures can be separated. Here's a few of the techniques we're going to talk about. Filtering, centrifuging, decanting, evaporating, distillation, and chromatography. And we're going to do some of these in class. Some we've already done. Some we really can't do because we don't have the equipment to do those things. First we'll talk about, I think what's down here, our centrifuge. Our centrifuge is something centrifugal. Centrifuge means going in a circle. So this is something where this machine is set up with maybe test tubes in here, and when I turn it on, it's going to spin extremely fast, causing what's called a centrifugal motion or centrifugal force. We use this in blood samples a lot. Well, we don't, your hospital will if they're doing a lab test or something, where they take your blood, which is a colloid, and it will not settle out by itself, but they want to separate it. They want the plasma away from the other stuff. And they'll put this in the centrifuge, and they'll centrifuge it out, and you get these different layers of your blood. And you can see this is a regular sample, and the second one over here has been centrifuged. So the difference when you start seeing those different layers. So the heavier, more denser things, the bigger particles, go to the bottom. And the smaller particles stay on top. That's how a centrifuge works, centrifugal motion. We also have something called chromatography. This separates the components based on how fast those molecules will move in a mobile phase along a solid phase. And we're going to try doing some of this paper chromatography in class. I start with an ink spot, and I put this in water. Notice the water is only down here at the bottom, but the water is going to kind of be absorbed. It's going to be absorbed by the paper and get pulled up. And when it pulls up, the paper, it carries these other things with it. The things that dissolve, these are more water soluble. The farther they move, the more water soluble they are. Something that doesn't move at all is not water soluble. Distillation is another form of separation. This uses the boiling points, physical property. It can separate components based on the physical nature of their boiling points. If they have a lower vapor pressure, they're going to evaporate first, and they'll be removed from the solution. It's called the distillate. So things that can boil fastest will boil up, and then they'll be condensed, and they'll be carried over into here. We can also do this with oil. Again, crude oil, it comes in a very thick, oily substance, very viscous material. It's heated up to a very, very high temperature, and things that have a vapor pressure, they can easily be distilled. Low melting points, low boiling points are taken off the top, and these are the heavy things on the bottom. Okay, these are things that have high boiling points. It takes more energy to boil them, so they don't go as far up the column. Now, sometimes we want to know how much of something is in the solution. How much solute is there in the solution? So there's some different ways we're going to calculate this. We'll talk about molarity tomorrow in class, but for today we're going to talk about this thing called parts per million. Now, if you remember a million, if I just write out a million, it looks like this, one with 6 zeros after it. That's a million. If I had $1 million, that's how many zeros would be after my dollar sign. So this is useful when I'm talking about impurity that is a very, very small amount. Often it's used in pollution or food contamination, something that should not be there but is there in a very, very small amount. The way it's expressed is the concentration over a million is the amount of the solute over the amount of the solvent. The way you're going to calculate it, if I want to know the concentration in parts per million, I take the grams of solute divided by the grams of solvent times parts per million. 1 times 10 to the 6th is a million. And that's going to give me my parts per million. So here's a problem. If I have a chemical analysis showing there's 2.2 milligrams of lead in 500 grams of water. Lead's not a good thing. It's a contaminant. It's a pollutant. It's hazardous. We want to keep that out of your water. But let's say that we found some in there. I want this measurement in parts per million. Because that's how scientists talk about things. If they're trying to talk about this sample from the lake or from the river, from the drinking water, they want to talk about it as parts per million, not as milligrams of lead. Because that depended on how much water I used. We want to make it more of a ratio that doesn't depend on the amount you start with. So I take my 2.2 milligrams times 1,000 grams, sorry, not times, divided by divided by 1,000 milligrams per gram. So I need to turn this into grams, and I get 0.0022 grams of lead. Now the next step then is to change this into my parts per million. So my grams of lead, I have trouble writing today, 22 grams of lead divided by, remember we said it was divided by the grams of, everything has to be in the same units, grams over grams. So my solvent then is the water, is the solvent. That's what the lead is dissolved in, times 1 times 10 to the 6th, so times 1,000,000. When I do that, I find that the concentration is 4.4 parts per million. So I could report that as a laboratory analysis, and I could report that to federal agencies or people who have asked the drinking water be tested, and this tells them how concentrated it is and how bad it is. There's more practice problems on page 461. You can take a look at those tonight. We will do those in class tomorrow to show you how to do some of these on your own. So remember, write out your vocab, write out your flashcards if you need to, and pay attention to those different methods for separation. We'll do some labs, we'll do some practice problems in class.